To all my viewers, feel most welcome into our today's discussion, whereby we are going to discuss about finding the Laplace transform using the second shift theorem. I've discussed on how you can go about the first shift theorem, but here now we want to discuss about the second shift theorem. And when it comes to the second shift theorem or the second derivative using the Laplace and transform, we understand that the theory states that the Laplace transform of our function f of t is equals to our function f with respect to s. To mean that we are going to convert the Laplace transform of a function t with respect to the algebraic function, which will be equals to s. Since it is very easy to simplify our functions of s, then we can come and say the Laplace transform of our function t to a power of n, we come and multiply by our function f of t is equals to, here we are going to have a negative of 1 raised to a power of n bn all over raised to a power of n. Here we come and multiply by our function f of s. To mean that the first thing that we need to understand about this second shift formula is that we must first get the Laplace transform of our function f of t, which will be equals to a function f of s here. After getting the function f of s, we come and find its differential, its derivative. That is the reason as to why we are referring to it as the second derivative using the Laplace transform, because it entails the part of finding the derivative of our function here. Let us now get into our first example. You can be told to find the Laplace transform of t exponential 3t using the second shift theorem. The first thing that we agreed on, it is going to take this kind of a formula. But when we check to the power of t here, it is a power of 1. To mean that we are going to have negative 1 raised to a power of 1, because that is the power of t here, d to a power of 1 all over d s to a power of 1. We come and multiply by the Laplace transform of our function f of t here. That is the reason as to why we are having f of s. And when we get the Laplace transform of our function f of t here, the Laplace transform of exponential at, positive or negative, is always equals to 1 all over s, negative or positive of a. This is the Laplace transform of that exponential. To mean when it comes to our function here, we are going to have the Laplace transform of exponential 3t. Since it is a positive here, we are going to have 1 all over s. We subtract from positive takes the negative, negative takes the positive. So we are going to have s, we subtract from a, and our a here is equals to 3. So this is the Laplace transform of our exponential here. And we are going to have the exponential is going to be the Laplace transform of our function f of s is 1 all over s. We subtract from 3. Let us now find here the derivative of this function. We can either decide to come and rewrite it in this form. As we subtract from 3, here it is going to be a power of -1. Since it was a differential here, let us now find the differential of this function. And we are going to have -1. When we differentiate this function here, we are going to have -1. We take this negative down here. -1 is outside. We take this -1 down here. We come and rewrite everything within the bracket as we subtract from 3. -1, -1. And then we come and get the differential of what we are having within the bracket. When we differentiate s, we are going to have 1. When we differentiate -3, we are going to have 0. And this is how now we are going to use the chain rule in finding the differential of this function. Here now we are going to have -1 into negative multiplied by the negative is going now to be a positive of 1. Here we are going to have s. We subtract from 3. Everything will be to a power of 2. And here we are going to have 1. And finally, our answer we are going to have 1 all over, because we understand when it is raised to a negative here, our function here is raised to a negative. We are going to have s. We subtract from 3. Everything now will be squared. And now finally, the Laplace transform of our function t exponential 3t is equals to 1 all over s. We subtract from 3. Everything squared. At this point, you can either decide to use the chain rule if you know how to go about the chain rule, or you can decide to use the quotient rule, whereby in the quotient rule here we are going to take this term as our u and this term as our v. We understand that dy with respect to dx is equals to v du, sorry, let me write it here. Dy with respect to dx is equals to v du with respect to dx. We come and subtract from u dv with respect to dx. Everything will be all over v squared. And you go about this one, you will get your answer the same as what we are having here. So you can try to use the quotient rule to go about the same working from this point. Let us now get into our second example. This is now our second example, whereby you can be told to find the Laplace transform using the second shift theorem. The basic thing that we need to understand about the second shift theorem is about the formula, whereby we say that the Laplace transform of t to a power of n, we multiply by our function f of t is equals to, here we are going to have negative of 1 raised to a power of n dn all over ds. We come and multiply by our function f of s. This is our second shift theorem formula. Let us now get into our working, whereby we are having the Laplace transform of t cos 5t is going to be equals to, here we are going to have -1 raised to a power of 1 d raised to a power of 1. Here we are going to have a power of 1, And then we come and get the Laplace transform of our function cos 5t. The Laplace transform of cos 5t is equals to s all over s squared we add to 25, because there we are going to have a squared. And now here we are going to have s all over s squared we add to 25. Here we are having the differential with respect to our Laplace transform of cos 5t. Here now we are going to use the quotient rule. And when it comes to the quotient rule, s will take the u, and here our denominator is going to take the v. What is the quotient rule? The quotient rule, we understand that d with respect to ds is equals to, we are going to have v du with respect to ds. We subtract from our u dv with respect to ds, and everything is going to be all over v squared. Let us now have all the parameters that we require. We understand that our u is equals to s. Our du with respect to ds is equals to 1. Our v is equals to s squared we add to 25. Our dv with respect to ds is equals to 2s. Let us now get back into the quotient formula and insert all the parameters that we are having here. And now we are going to have d with respect to ds is going to be equals to v. Our v is equals to s squared we add to 25. v du with respect to ds is equals to 1. We subtract from our u. Our u is equals to s. dv with respect to ds. dv with respect to ds is going to be equals to 2s. Everything all over v squared. Our v squared is equals to s squared we add to 25. But everything is now going to be squared. Remember that it was the differential of our function here, but we were having a negative of 1. Let us now let us now include the negative of 1 to mean that the Laplace transform of now t cos 5t is going to be equals to negative 1. Here, when we open the bracket, we are going to have s squared we add to 25. We subtract from here, we are going to have 2s squared. Everything is going to be all over s squared we add to 25, everything squared. Let us simplify what we are having within this bracket. And now we are going to have the Laplace transform of cos 5t is equals to, we are going to have negative 1 into s. Here we are having a negative of 2s squared. We are going to have a negative of s squared. We come and add to 25 all over s squared we add to 25, but our denominator will be squared. Negative 1 multiplied by everything on the numerator, we are going to have s squared we subtract from 25 all over s squared we add to 25, but on our denominator everything was squared. And this is how you go about finding the Laplace transform using the second shift theorem of our function here.